Right, A-level maths quiz question. Imagine that this was the final £1,000,000 question on Who Wants to Be a Millionaire, and you had to answer this, get £1,000,000. Right, this is the question, right? Are you ready? Now, it's not quite a Who Wants to Be a Millionaire question because it's just two options, yes or no. You just got to write down yes or no, right? It's yes or no question, yes or no. Everyone comment your answer when I say the question. I'm going to say the question. You've got 10 seconds to answer. You ready? Here we go. Question is, are all points of inflection stationary points? I repeat the question. Are all points of inflection stationary points? You got 10 seconds. 10, 9, 8. Comment your answer now. 7, 6, 5, 4, 3, 2, 1, 0. Stop. Over. Stop. Okay. So if you said yes, all points of inflection are stationary points, yes, you unfortunately will not be winning £1,000,000. If you said no, all points of inflection are not stationary points, unfortunately you will not be winning £1,000,000 too, because I don't have £1,000,000 to give you, but you're right. So the answer is no. So let's talk about this in detail. So a stationary point, starting with a stationary point is a point on a curve where dy by dx equals 0. Or if it's written as a function, f dash of x is equal to 0. So what does this mean? So let's say you had some kind of curve like this. dy by dx or f dash of x, this is your gradient, right? It's a measure of your gradient. We need the gradient to be 0. So if we look at this curve here, right, we can see that at this point here and this point here and this point kind of here, the gradients here are 0, right? Draw a tangent, 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 gradients are 0. So you call these points stationary points. Now, a point of inflection is a bit harder to write as a definition, but a point of inflection essentially is a point on a curve where the second derivative d squared y over dx squared changes from positive to negative, or instead negative to positive. So let's go through what this really means. So a classic example of a point of inflection is with the curve y equals x cubed. So this point in the middle here would be a point of inflection. Why is that? So to understand this, we need to really understand what this means. What does this actually reflect in reality? So we know that dy by dx is the gradient, right? So dy by dx is a representation of the gradient of a curve. So, I mean, for example, dy by dx here is going to be whatever this gradient there is. So dy by dx here is actually going to be 0, and you can prove that by differentiating this, plugging in x equals 0, and you'll see that dy by dx there is 0. So we actually know the gradient here is 0. So this is a stationary point. So it's a stationary point, but actually it's also a point of inflection as well in this scenario. Now, I want you to think about this second derivative as the kind of quote acceleration. I use two lots of speech marks here because it's not really the acceleration of the curve, but that's how I think about it. If you think about it like mechanics, it will help you understand this. So I want you to think about this curve as kind of like a funfair roller coaster ride, right? So we're traveling from down here, we're starting down here, we're working our way up. Do you kind of see that we're, quote, decelerating, right? So that's how I think about it, right? So we're kind of decelerating, we're slowing down. The y values are slowing down. Yes, the change of the y values is slowing down. So what we would say here, we would say for this part of the curve that the second derivative is negative because we're kind of decelerating. Hopefully that makes sense because you're slowing down, right? You're not accelerating upwards, you're kind of decelerating. Now for this part of the curve here, so this part there, you're accelerating, so you're accelerating. So here, your second derivative would be positive at this point here. Now the idea is that at this point, your second derivative is going to be 0. So there is a transition. At this point here, there is a transition from a negative acceleration to a positive acceleration. So when you have a transition where your acceleration goes from negative to positive or vice versa, this transition point is the point of inflection. So again, this point x equals 0 is both a stationary point because the gradient is 0 and also a point of inflection because of the transition. Now, if you've done this in class properly, you will have seen the technical terminology for this. So when the curve has a negative second derivative, you call this concave. So this is a concave part of the curve. So this part of the curve is concave, and you call this part of the curve here convex, where your acceleration is positive. So this is convex. The way that I remember it, concave is like you're going into a cave, like, so imagine like that's a cave, you're going into a cave, and convex is like a kind of V shape, well, U shape, but kind of a V shape, right? So convex, that's how I remember it. So obviously a consequence of this is that a point of inflection must have a 0 second derivative. So the second derivative here is going to be 0 at this point of inflection. Now, something that is really important to mention, just because the second derivative is 0, it does not mean that this is a point of inflection. I'll show you now why that is true. So I've sketched here a graph y equals x to the power 4. It's kind of like a quadratic, but what you'll notice if you go to like a graphing software, the flat bit at the bottom is more flat there. So what you can do is you can differentiate this. So hopefully we know from differentiation that this is going to be 4x to the power 3. You can then differentiate it again. So the second derivative is going to be 12x to the power 2. Now, if you plug in x equals 0, plug it into there, right? 12 times 0 squared, you would get 0. But that is not a point of inflection, is it? It's a minimum point, because it's a minimum point. It's not a point of inflection. So just because the second derivative is 0, it doesn't mean that it is a point of inflection. But a point of inflection does have a 0 second derivative. So just an important distinction to make. Again, a point of inflection is a point where there is this transition. With this curve here, we do not have this transition. This is a convex curve, right? This is always convex. We're always accelerating, right? Because we're accelerating upwards, right? So the second derivative is positive here and it's positive here. There is no transition. Now then, so going back to that first quiz question at the start about not all points of inflection being stationary points. So what you just saw with the XQ graph was that the stationary point was the point of inflection, but that's not always true. And let me show you a famous example to show you that that's not true. So I've sketched here a normal distribution curve, and you don't need to know this for A-level maths, but the equation for a normal distribution curve is this there. So sigma is your standard deviation, mu is your mean. That is the actual curve for a normal distribution. Now, one thing you do need to know for your A-level maths, and it is in your syllabus, and here it is in the syllabus right here. Students should know that the points of inflection on a normal curve are at x equals mu plus or minus sigma. So mu is the mean for a normal distribution. So we have points of inflection. I mean, the curve's really bad here, but you should have points of inflection here. So the idea is that this here is mu take away the standard deviation, and this here is mu plus the standard deviation. So you do need to know this fact that a normal distribution curve has 2 points of inflection. Now, even though we do have 2 points of inflection here and here, are they stationary points? No, because can you see these green tangents I've drawn in here, right? So drawing a tangent, is the gradient of those tangents 0? No. Remember, for a stationary point, the gradient has to be 0. The gradient is not 0 there, and it's not 0 there. So they're not stationary points, but they are points of inflection. And the reason for that is basically because if we look at this point here, right? I mean, the curve is really bad. I've not done a very good curve. I'm going to redraw the curve again, actually. So let's just start with this left-hand point here. So do you notice when we're going down this roller coaster, we are really decelerating, aren't we? Like we're decelerating. But then all of a sudden there's a transition, because now after this point here, we're starting to accelerate back up. So this point of the curve, this part of the curve here is convex. The second derivative is positive. But this part of the curve, we have a concave curve. The second derivative is negative. So again, we've got a transition here. Same kind of logic here. There is a transition with the second derivative. So we've got a negative second derivative, and then now we're starting to accelerate upwards. So that is a point of inflection, but they're not stationary points. Now, I highly, highly doubt an exam question will want you to prove that those 2 points on a normal distribution are points of inflection. However, I say that there is nothing beyond A-level maths that you need to know to do that. So everything in the A-level maths syllabus is enough to teach you how to prove that 2 points on a normal distribution curve are points of inflection. So if you want me to do a video going through that proof, because again, it's not beyond A-level maths, it's tricky, it's going to look really messy, it's a very horrible, like horrible numbers and horrible algebra, but it's not beyond A-level maths. So just let me know, just comment below 1, comment the number 1 if you want to see that proof, and I'll do that soon.